Hello 10th grade. Here we are with lesson number 5, reaction rates. We're done with our talk about energy and reactions. We'll of course still be tying back into that, but that part about enthalpy of the unit is over. The second half of our unit is focusing on reaction rates. So this is a kind of an introductory lesson. It's not a very long one. We'll be getting into more detail about graphing reaction rates next lesson. So at this point, by the end of this lesson, we'll have beginning number 3 done. So that was this one here. How can good experimental design help us to accurately analyze chemical reactions? Okay, so you can tie that into experimental design we talked about for calorimetry in the enthalpy part of the unit, as well as our lessons today. Okay, here's your template. So what is reaction rate? There's a couple drawings here for collision theory, and then reaction rate is about experimental design and kind of things we're going to be doing for that. There are no practice questions for today. You have the Hindenburg assignment to do instead. I'll be doing more practice work with graphing and stuff for reaction rates next class. Okay, so first thing, what is reaction rate? Have you guys ever used a glow stick? I know when I was a kid, we used to get them that could be made into necklaces and bracelets and stuff for like carnivals, for Canada Day events, for camping, that kind of stuff. Originally, these were invented for search and rescue, for safety. So you could have a glow stick if you were lost while you were hiking or something like that. But now people use them for lots of other things as well. So how the glow sticks actually work is they mix hydrogen peroxide, H2O2, which is inside a little glass tube inside the glow stick, with a chemical called phenyl oxalate ester and a fluorescent dye. The fluorescent dye differs based on what color your glow stick actually is. And when you break the little glass tube inside by bending the plastic glow stick, you're going to mix the two reactants and cause a chemical reaction. So take a look at these 3 glow sticks here. They're same glow stick in different containers. Why do we think they're not all glowing with the same brightness? Well, these are all in different temperatures of water. You can see the first one here, there's ice in that water. So we have really cold water, we have room temperature like cold tap water, and then we have room temperature water. So temperature is one thing that has a direct effect on reaction rate. And reaction rate, the full definition, is the speed at which reactants are converted into products. So it's per unit time, this process. Okay, so chemical reactions happen at a big variety of reaction rates. So we have 2 reactions here pictured with very different reaction rates. Why do you think those rates differ so much? We have an explosion here, reaction between pure sodium and water, which I did that with my grade 9s this year, not that much to get a huge explosion, but we did it with grade 9. I don't know if you guys did it last year or not. And then here is a banana ripening over time with ethylene reacting in that reaction. So why is it a different rate? Well, the reactivity of the reactants is part of this. So we know that sodium is very, very reactive. Group 1 metals are very reactive in the periodic table, especially with water. We know that enzymes and catalysts can be things that cause it to happen. Ethylene is going to react with the banana to help it make it ripen. But ripening of fruit is meant to be a slower reaction. You don't want it to happen instantly. If you think about evolutionary context here, fruit is meant to help carry seeds from the fruit to different new locations. And we don't want it to happen too quickly. We want it to happen so that we have the seeds being dispersed continually over the entire over the entire season for that particular fruit or vegetable. And we can measure reaction rate in a couple of different ways. By the amount of product we're producing per unit time, or by the amount of reactants consumed per unit time. So either of these will give you the same thing because, of course, as product becomes reactant, it's going to be going, and the reactants will become product. So either way you measure it is still going to be accurate to that particular chemical reaction. Okay? And the method you used to do this depends on the feasibility for each component. Is it easier to measure reactants or products? What kind of equipment do you have? What's being made? That kind of stuff. Are you going to lose a product so quickly you can't track its production rate? That kind of stuff. So let's look at collision theory. And I want you to draw this image for sure. And depending on your background in chemistry and how strong you know this, you can also draw this one here. So particle theory is in this top reaction. Something you should have learned in middle school, and hopefully you have learned. But it's the idea that all matter is made of particles, and those particles could be atoms, compounds, ions, molecules, any of those things, and that matter is constantly moving. So you look here in the solid, they're moving a little bit, little vibration lines, and liquids are moving more, and in a gas moving even more. Okay, the degree of movement of these particles depends on the state, so solids move least, then liquids, and then gases, as well as the energy. The more energy it has, the more it's going to move, which is part of why energy causes sort of state changes from solid to liquid, liquid to gas, and then if it cools down, it loses energy from gas to liquid, liquid to solid. The other thing that affects the movement of particles is the relationship with other particles. There's other particles around it that are causing it to be attracted towards them and move in other ways that can cause different things in their movement as well. So to understand collision theory, you have to understand the idea that all particles are moving. Particle theory has to make sense to you. And collision theory is key to understanding chemical reactions. So collision theory tells us that a chemical reaction, that for it to happen, the particles involved have to not only collide, but they have to collide with sufficient energy and the correct orientation to face the right direction to have the sufficient energy and situation to be able to break bonds and form new bonds. Okay, so you look at this picture here, this first reaction, the particles are not moving fast, there's not enough energy to actually make a reaction. They're going to bounce to the but you don't have enough energy to actually break the bond enthalpy and break the bonds and make new bonds. Here, we have more energy, a little more vibration lines here in the collision, but they're not hitting the right parts. So the hydrogen here, so the oxygen it's not going to react with the nitrogen. It has to be the carbon and the nitrogen reacting. So they're going to bounce off, no reaction. Here we have enough energy and the right direction. So the nitrogen and the carbon are going to hit, and I get carbon dioxide and I get nitrogen dioxide. Okay, and that's the actual reaction. So it's the energy and orientation both are required. So draw this for sure. I recommend use the colors to help show the different kinds of molecules here. Okay, let's look at an example of this. So here we have a wooden splint that's undergoing a combustion reaction. In the first image here at the top, it's being burned in air, just the air and the atmosphere around us. And you see the flame, it's burning. And then the second, we put it down to this vial, which contains pure oxygen. Here's the chemical reaction of an organic compound combustion. So organic compound, this is the wooden splint. And then we have presence of oxygen, it gives carbon dioxide and water. So how can you use collision theory to explain the difference between these two images? Which reaction is occurring more quickly? Well, definitely the second one. There's a lot bigger flame, and light or heat produced is a sign of chemical reaction. So a lot more reactions happening here. And how can collision theory explain this? Well, there's more oxygen present. There's more oxygen, it's more likely to have a collision between the oxygen and the wood of the splint. So the air we're breathing does contain oxygen, of course, else we'd all be dead, but it only contains about 20% oxygen. The rest of the air is about 78% nitrogen, 0.9% argon gases, 0.17% other gases, and 0.03% carbon dioxide, so very low CO2. And that amount of oxygen is going to have a direct effect on the rate of reaction. Now, if combustion reactions happen so much more quickly in the presence of pure oxygen, would it just make sense to always use pure oxygen when we're doing a combustion reaction? On your stove, at a campfire, any of those things, the best to always have pure oxygen? Why or why not? Well, we probably don't want to make the reaction happen that quickly most of the time. First of all, it's going to produce too much energy too quickly and can be dangerous. Second of all, once the fuel runs out, once we've completely used up our organic compound part of our reaction, there's no more product being made. So if you want to have that heat or light produced, you need to kind of slow down the reaction. And there's some situations in which people who are doing like a smoking or a slow burning barbecue kind of thing, they'll try and make a reaction happen with less oxygen enough to keep the reaction happening, of course, but less oxygen to try and slow it down a bit, so you get a lower heat over a longer period of time. Okay, so now we know about reaction rates. How can we actually calculate reaction rate? Well, we're going to talk about one specific example here to analyze this. So we already talked about that in theory, the way you can do this is you can measure either the consumption rate of the reactants or the production rate of the products. But how in a lab will we actually do this? Well, we're going to look at a reaction here of calcium carbonate and hydrochloric acid. It's the balanced equation here. I have calcium carbonate and hydrochloric acid producing calcium chloride, water, and carbon dioxide. So let's look at the reaction here. Which one do you think gives us the best idea of rate if we do reactants or if we do products? What do you think is going to be better? Well, we should definitely be doing products because the reactants, you can't, once we mix together, it's hard to, you can't measure their consumption rate. It's too hard to separate them. If you look at this little video here, here's a clip of the actual reaction happening. Oops. Okay, here we go again. So here's our calcium carbonate as a powder. Sometimes you'll see it as chips as well, like bigger chunks. It's instantaneously reacting. So it's happening so quickly, I can't really measure the loss of my calcium carbonate or the loss of my hydrochloric acid or hydrogen chloride. So products makes more sense. Okay, what about, can we do water? Can we do calcium chloride? Well, if you look at the picture here, I have my calcium carbonate and I have my hydrochloric acid, and this is my reaction. I'm getting all these bubbles of carbon dioxide and my calcium chloride and my water. Now, calcium chloride is aqueous. That AQ means aqueous. It means it's dissolved in the water. So it's really hard to separate it. So if we look here, can we measure the consumption of calcium carbonate? Not really. The reaction happens too quickly. We can't get a clear measure of how much is being lost. We have to mix with the hydrochloric acid anyway to kind of have the reaction happening. Same thing with hydrochloric acid. We can't separate it from calcium carbonate because the reaction happens too quickly to do that. Calcium chloride, can we measure that production? Well, it's produced, we know it's aqueous, so it's dissolved in water. So maybe we could boil the water off, let the reaction happen, then boil the water off and measure the mass. But the problem is that's too slow to get a rate, and the rate is a measure per unit time. So we can't take we could take a sample every 5 seconds of the reaction, put it in a test tube, and then boil the water off. The problem is that reaction would still be happening, so you couldn't get an accurate measure of the rate. Can we measure water? How much water is being produced? Well, I don't have a way to do that without separating it, and that's just too challenging to do. So about carbon dioxide. Well, the part that makes this very doable is the fact that carbon dioxide is a gas, a separate state from everything else, so it's going to be separate from the other products, which are really easy to separate and look at. So carbon dioxide makes the most sense, and we can measure carbon dioxide production. It's going to be a gas, going to rise to the surface, it's going to be produced, and we can then collect it. So here are some ways of collecting the gas. We could have the reaction mixture in a Erlenmeyer flask here with a stopper, collecting the gas, and it's going to push the gas underwater and into some sort of container like this, graduated, so we can see the water level changing to measure the rate. And we're just measuring it right into the rate, the water level, as we keep track of time. Remember, reaction rate is the rate of change per unit time. This one, the second setup here has a little bit of some improvements and some not so great parts of it. So this is an improvement. We're able to make sure we can have the calcium carbonate in the bottom of my e-flask already and just add the acid directly without having to open and close the stopper, which means we're not going to be worried about losing any gas in the very early part of the reaction. And then I'm pumping the gas down below water and having into a chamber here. The problem here, though, is I have a glass jar with no measurement, no gradations. So if I had this part with this part, that would be ideal. Here's another option. On a scale, I can see how the mass changes over time, because what's going to happen is if I put cotton wool on the top of my reaction, I'm going to have gas leaving. The CO2 can leave, but nothing else can leave, which means as the mass goes down, I can measure the rate of carbon dioxide loss. So again, with a stopwatch, taking the mass every 10 seconds, it depends on how quickly the reaction is going to happen, and then measuring, that's a measure of the rate of reaction, how much carbon dioxide is being produced per unit time. I can also use a sensor for this. I can use a carbon dioxide sensor, have the reaction happen in a container, and I'm going to just measure the CO2 production. Be careful with this one because these cannot be exposed to liquids. You can also do a pressure sensor, the pressure of the gas. There's no gas at the start, so any gas being produced down here is going to produce increased pressure, and I can measure that as well for reaction rate. There's lots of options for measuring the gas, but you need to make sure that you think about any chemical reaction for reaction rate, what is most measurable and how can I do it. Okay, that's the end of the lesson here. So big idea number 3, make sure you do that in your notes. And your homework is upload a copy of your notes from today's lesson, including the Hindenburg reaction analysis assignment, which is for the energy reactions part of our unit. And of course, big idea number 3. The first 3 should be done after today's lesson. Okay guys, take care. We'll have the next one, but more about reaction rates, so more detail coming your way.